People often say so-and-so leads little introduction. I think this is particularly true in Sir Dave's case. He's been a distinguished professor of chemistry at Cambridge. He was a pioneer in making sure the government had comprehensive scientific advice. And when I say he was responsible for the foot and mouth outbreak, what I mean, he was responsible for making sure it wasn't worse. And more recently, he's been much involved in issues of science policy. So we're delighted to hear from you today. Please take it away.
Thank you very much, Mike, and it's a great privilege to be talking to you this evening. So I'm going to be talking about science-led policy, and I'm not just talking about climate change, but something a little more topical at the moment, which is global pandemics. So let me take you back to the point where I was Chief Scientific Advisor with Tony Blair. The only reason I left my wonderful job in Cambridge to go into government was because I wanted to have an impact on climate change. But before I could manage that, we had a foot and mouth disease outbreak. And I thought that was a big distraction, and I learned a very important lesson, which was because the foot and mouth disease outbreak was critically important to the government, to get in there and demonstrate how to get out of it became a wonderful way for me to work on my major objective, which was climate change. So let me start with the next slide by saying the 21st century has a set of challenges that are very, very different from any other challenges that civilization has ever had to face. The reason is that parameter in the middle, the big driver for change, is population. 1.5 billion total people at the beginning of the 20th century. By the end of the century was 6 billion. We're now approaching 8 billion. That figure will probably plateau off at about 10 to 11 billion by the end of the century, unless there are severe disasters between now and then. And each of the challenges represented in this little diagram is a major challenge for all countries of the world, and each country faces a different parameter of challenge. So let me just focus here on health as a major form of challenge, and I'm going to then go over to climate change. So if I could have the next slide. I developed something which was an in-depth foresight process, looking out into the future to see, first of all, what are the drivers for change around each of the topics shown here? And determining those drivers was a big job. But once you've got the drivers for change, you start working on developing futures, but not one future. You're not predicting the future. You have to look at very different forms of future. And amongst those, you will always find one that is much more attractive and one that is much less attractive than the others. So then it became a question of what government interventions can be made to create a more attractive future. That was basically the foresight projects. In the middle, at the bottom, you see flood and coastal defenses. That was one of the first program I started on, which was really because the British people are faced with climate change threats of many kinds, but the biggest of all is the flood and coastal defense threats to our island nation. And above that, detection and identification of infectious diseases was a project that emerged from the work I did on foot and mouth disease, but subsequently developed through work we did on SARS and other infectious disease outbreaks around the world. And so just starting with that first one, if I could have the next slide, the detection and identification of infectious diseases, you'll see that this was published in 2006. It was the biggest of all of those foresight programs I initiated and ran between 2001 and 2007. It was reported in 2006. 340 experts from around the world were involved. We had 30 different countries represented amongst the experts. Very much an in-depth focus on infectious diseases in plants, animals, and human beings. And we concluded from this that over the next 25 years, that is from 2006 onwards, we could see that a major pandemic would arise as a new virus emerged, probably from a wild species, a wild animal, with the virus becoming mutated into a human-to-human virus. These viruses are very animal-specific, but they can mutate and survive in other animals. And what we were looking at was the potential of just such an epidemic occurring as is now happening. And then we set in train a number of things that governments should do. And amongst the people working with us were people from the WHO, the World Health Organization, and in particular from other countries. We had people from China and Africa, not only because we believed that is where the next big epidemic might arise from, but also because we felt these were two areas of the world that needed at this point, 2006, some help in determining what governments should do when faced with these kinds of crises. Now, needless to say, this current pandemic emerged in China, and I would have to say that China managed this process extremely well. And the interesting thing is that amongst the countries that have handled it very badly is the United Kingdom, where this piece of work was initiated. And of course, this makes me feel exceptionally sad because we had the expertise, we still have it, we had the capability, but we also had a government commitment to set in place all of the processes we needed to manage a pandemic of this kind back in 2006. I'll come back to that later, but let me just move quickly on to climate change and talk to you in a very summary form about the development of climate science in the 19th century. So the next slide just encapsulates that development by mentioning three names of key scientists. The first is the great French mathematician Fourier, who in 1820 had the gall to say, I should be able to calculate the average temperature at the Earth's surface because I fully understand how much heat arrives at the Earth's surface from the sun, and I also know how much radiation takes place back into space from a hot body. And key to his calculation was the understanding that that radiation process depends on the fourth power of the temperature. So because of this fourth power, he felt he could calculate the temperature of the Earth very accurately by saying, quite simply, when the radiated heat is absorbed and then radiated back, when the sun's heat is absorbed and then radiated back into space, we reached an equilibrium heat for the Earth's surface, and that was the temperature he calculated. His first calculation yielded a number that was about 30 degrees too low. He didn't try and publish the paper until he had worked out that what was happening was that heat was retained by the Earth's atmosphere, was captured by it, much as a blanket over you when you're lying in your bed keeps you warm by keeping the heat radiated from your body back in your bed. Now, he didn't know which of the gases in the atmosphere was doing that. In fact, Fourier thought it was all of them, and all he did was feed in a coefficient, and many of us would say this was sort of cheating, a coefficient to get the right temperature as the average for the Earth. But along comes Tyndall, the Irish scientist, who in 1860 does an experiment in which he sees how much heat is observed by a piece of the atmosphere he put into a tube, put heat in at one end, radiated heat, and measure how much emerges at the other end. But he did his experiment, first of all, by removing all of what he thought were the impure gases from his sample of air, carbon dioxide, water vapor, methane. And so what he initially found was a Fourier coefficient of 0. So it didn't match with Fourier's result at all. But then he, fortunately, did another experiment with air as it is, with those small minority gases in the sample, and he repeated Fourier's coefficient very accurately. So the conclusion was that we had greenhouse gases, these are minority gases in the atmosphere, and critically, that oxygen and nitrogen, the main constituents of the atmosphere, do not absorb any radiated heat. Now, from quantum theory, we can understand, and if anyone wants to, I can try and explain it to you, why oxygen and nitrogen do not absorb radiated heat, but these slightly bigger molecules, nonlinear, many of them do. Then we come to 1898, when the Swedish scientist, one of the first Nobel Prize winners, I would describe him as a physical chemist, Arrhenius, calculates what effect fossil fuel burning would have on the temperature at the surface of the Earth. So what he's saying is, my goodness, if we keep burning forests, if we keep removing forests, and if we keep burning fossil fuels, the carbon dioxide level in the atmosphere will increase, and that must mean that the temperature will increase. So he's just using Fourier's equations, he's using Tyndall's coefficients, and calculating that if the carbon dioxide level were to double, the temperature rise would be about 5 degrees centigrade. This is the basis of the mathematics that is currently used to calculate the temperature rise due to greenhouse gases in the atmosphere. There are complications, and they are very serious, some of them. Cloud cover, for example, clouds that are white in daylight reflect sunshine back into space. Clouds that are black absorb the sunshine. And so the whole process is a little more complicated than the calculation of Arrhenius would have computed. But nevertheless, if I tell you that the world's biggest computer today is providing a number of about 5 plus or minus 2 degrees centigrade. So essentially, by the end of the 19th century, climate science was pretty well understood, or at least the basics were. If I could have the next slide. I come to the point where I'm chief scientific advisor. In the year 2003, we had the worst disaster in Central Europe on record as measured by the number of fatalities. And this was a heat wave, a very hot summer in 2003. And in that summer, hot summer, excess deaths were about 50,000. Interestingly, about the same number of excess deaths that we have in the UK today following the coronavirus outbreak. But this major heat stress disaster in Central Europe is represented on this curve. On the vertical axis, I've got temperature change from the average around 1900 up to that 2003 period. So I got the Met Office to produce this graph in 2003 for me. So shown in black is the average Central European summer temperature, and you'll see that 2003 was a very extreme hot weather event. The previous hot weather, you can see the peak in 1947. So then we superimposed on this curve the Met Office's model for predicting tomorrow's weather, the weather in a week's time, the weather in a month's time, etc. And that model at this point had just had included into it greenhouse gases. So we could model the temperature going forward in time out to 2100 on an emission scenario. We had to choose an emission scenario. We chose medium to high emissions. And if I tell you that today we are absolutely on the medium to high emission scenario up to the present day, apart from the fall due to coronavirus and what has happened this year. So what you see in red are a repeat of the Met Office model run backwards in time and forwards in time to 2100. And the repeat is every 6 weeks they reinitiated the program so that what looks like, what is the weather, which is their weather prediction for tomorrow, etc., for the whole world, what looks like noise is the weather. And if you're 6 weeks out from when the program was initiated, it is absolutely noise. So the overall trend is due to greenhouse gas changes. And you'll see that the model run backwards in time gives a good description of Central European summer temperatures back to 1900. And therefore, this gives us more trust as we run the model forward in time that the model is giving us a valid prediction. And you'll see that in 2045, the average summer temperature in Central Europe will be the same as that extremely hot summer of 2003. So in the first instance, this encapsulates the challenge of climate change. But in the second instance, I want to stress the importance of extreme weather events. So if we had an extreme weather event, an excursion of the kind that occurred in 2003, in 2050 or thereabouts, we would have a very severe hot summer in Central Europe. So that's the argument for taking action on climate change. As we move forward through the century on medium to high emissions, you'll see that the predicted temperature rise in the summer in Europe, Central Europe, is about 6 degrees centigrade above that in 1900. So the challenge to humanity is extremely severe, but I really want to stress the extreme weather events, those unusual spikes, are the real challenge on this rising background. We may adapt to the rising background, but much more challenging to adapt to these extreme weather events. The next slide takes me forward from that point. I joined the Foreign Office to be the climate envoy, the climate ambassador for the United Kingdom, so running climate negotiations, etc. And as I joined, we set up this program, which was to take the lessons learned from that 2003 experience and have a climate change risk assessment program. The Intergovernmental Panel on Climate Change focuses not on extreme weather events, it focuses on the most probable future that we can be faced with. And what I wanted to do was bring into the climate change analysis a risk assessment. And so I brought in risk assessment experts, the actuaries who work in the insurance and reinsurance industry in particular. And I engaged with a number of countries. It was a global piece of work, but in particular with the governments of India and China. And the reason I did that was because whatever else the rest of the world does, what India and China does going forward in time over this century would be critical in how we manage climate change. And the report I'm showing you the cover of here is on the Foreign Office website. It was printed for us in 2015. So in early 2015, this report was made available. And the report demonstrates the nature of the challenges that both China and India are faced with. So on the group of about 100 experts we had, we also invited China and India to bring their expert community who advised the government on actions. And this included admirals, generals, people from their security services. Each government was taking this very seriously. And the work has been continued in both countries to the present day. After we made this report, and it was published in 2015, they took it into separate endeavors. The Indians took it into their security services and their defense services, and the Chinese did a much more open continuation of the risk assessment for China. And they brought me back to evaluate how they were doing every year. Now, the point I'm making here is quite simple. We asked each of the countries to put forward four risks that they would like the actuaries to calculate for them. And then we used the best of the climate analysis available and used, again, a medium to high risk scenario to calculate forward in time how that risk would change as temperatures rose, as sea levels rose, etc. And there were no surprises in some of the risks they asked us to analyze. Heat stress, both countries will suffer very severe heat stress, rising sea levels. Calcutta, we concluded, will be the first major city in the world to be unlivable due to frequent flooding, so frequent that it would be more than once a year. And I'm talking about a period not too far in tens of years from where we are at the present time. And across the Ganges mouth from Calcutta is, of course, the country of Bangladesh, and roughly 2/3 of Bangladesh will be unlivable by that time. So, in other words, in that part of the world, there would be roughly 160 million people plus looking for somewhere else to live. And that, of course, is what is of great concern to India. So amongst the risks that we were asked to analyze that we did not expect was the Chinese government coming back and saying, what is the probability that all of our rice crops fail in 1 year? And if we look at that probability at the present time, this is almost the same as the probability that your house will burn down in 1 year. And you know these actuaries will give you a probability on that. They, however, became very alarmed when we showed that a temperature rise of 0.5 to 1 degree above the present level made that probability for a given year begin to approach 1% and then go beyond that. And as the temperature rose above that, an exponential rise in the probability term of that happening in a given year. Quite simply, the reason is because the rice plant, as it grows, when it comes into flower, if the temperature is above a certain level for 3 days or more, the rice plant produces no rice whatsoever. So we used that to perform that analysis. So the point about this exercise was to demonstrate that when you do a risk assessment, the risks to all countries are much more severe than if you look at the most probable risk. And I know that sounds very self-evident, but this was the first time this had been done in that sort of detail. The next slide just says, then we came to Paris. Unfortunately, by this time, we had China and India fully behind us. We had Obama in the White House. I had an enormous operation. I had 165 full-time equivalent climate attaches in our embassies around the world. I had made 96 official country visits in the run-up to the Paris meeting in 3 years. And each of those visits was a bilateral negotiation. By the time we reached Paris, I was very confident that we would reach an agreement. And in particular, we agreed not on the 2 degrees centigrade above the pre-industrial level as the maximum, which we should try to stay below. We switched that to 1.5 degrees. And I'm very pleased to tell you that that was the British government that really pushed that 1.5 degrees, and I'll explain that in a moment. So in the middle, we have emissions from each country. In order to give President Obama the chance to vote with us on this, we knew that we had to make a non-top-down process. That meant every country had to voluntarily say what it would do to reduce its emissions. We knew the sum total of that reduction would not achieve the first objective, that long-term goal, and so we also put a review mechanism in place. That review mechanism comes to a head this year, 5 years after that agreement was reached. And in that review mechanism, what we intended was that we match up what each country was doing, adding that together to see that it stayed within that 1.5 to 2 degrees centigrade target set as the long-term goal. That is the objective this year. Now, this year, the COP meeting is in Glasgow. The British are in the presidency, but because of the coronavirus outbreak, it has been moved from November this year to next year. And it even looks as if it may not happen until after the summer of next year. Gives us a little bit more time to try and get an agreement that will match up to the first objective. And I have to say, that if President Trump is re-elected, there is no chance of that happening because the United Nations proceeds by unilateral agreement. And President Trump, although he said they would leave the UNFCCC process, has not done that. And if he stays in, that would obviate the process, let alone the fact that Brazil, Saudi Arabia, and until recently Australia have also been blocking progress. So I'm going to take that question on board. How do we get a bit of progress out of this, despite the fact that we can't really anticipate an agreement at COP26 that will match up to the target? Let me just take you back to that first goal, the 1.5 degrees centigrade. I'm going to say there was a Pacific Islands Forum of heads of governments of the Pacific Island nations in Papua New Guinea in 2015, ahead of that Paris meeting in November. And the British are represented there, and I was sent as the representative for Britain. All of the island nations were represented by their heads of government, in addition to Australia and New Zealand. At that meeting, the Australians and the New Zealand governments both said that the islanders should manage to increase their economic wealth, and if they did that, they would be able to manage any challenge from climate change. Now, many of the islanders knew that they would not be able to survive. Many of them would be underwater with rising sea levels by the end of the century, and they were pretty unhappy about that. I managed to get a message through to number 10 saying that I proposed to support the islanders in their efforts to stay within 1.5 degrees centigrade. The next slide, I hope, shows you a picture. It's a picture of myself making this speech that I had just that moment been given permission to make, saying, we too are an island nation and we will back your endeavor to put 1.5 degrees centigrade into the agreement. Now, I'm going to say that that was quite an achievement to get the 1.5 degrees centigrade target up there, even though it is exceptionally difficult to see how we're going to do that. But let me just show you on the next slide how difficult this really is. If I show you here, I apologize that the axes aren't labeled. The vertical axis is billions of tons of greenhouse gases emitted per annum, and the horizontal scale, years 2010 to 2050. In black, the baseline figure before actions on climate change. In yellow, the policy trajectory as before we got to the meeting in Paris, and then in red and green, different policy trajectories as emerged from Paris. And you can see that those trajectories are way above either the 2 degrees centigrade range or the 1.5 degrees centigrade range. So we are nowhere close to achieving our objectives. And what we need is to see a very steep fall in greenhouse gas emissions if we have any hope at all of achieving the 1.5 degrees centigrade target. I'm just going to interpose this bad news by giving you some good news. When we met in Paris in November 2015, actually, the good news was that for the whole world, the installation of clean energy technologies for producing electricity as new installations was more than 50% for the whole world. If you look at new installations for electricity production, more than half of them were from renewables, mostly from photovoltaics, but also from wind. And this was the result of national actions. I'll show you on the next slide. The falling costs for clean energy technologies from 2008 to 2014. Actually, this process began in Germany in 1989 when they introduced feed-in tariffs. And these feed-in tariffs were a massive subsidy to any customers in Germany, individuals or companies, who were prepared to use renewable energy systems to produce electricity for themselves. And any excess electricity they had, they could sell back onto the grid, and the subsidy was very large indeed. The idea was to create a new market for these clean energy technologies, and as that market grew, the prices of the new energy technologies fell. Britain joined this process in 1997, and the process was subsequently joined by other countries in the European Union. California came in a bit later. The result was the market that was created for these costly clean energy technologies meant they no longer were costly, and for each of them, they became very competitive in the marketplace. And so for the rest of the world, it became market advantageous to move into clean energy technologies, and that was the biggest driver of all. So even before we had an international agreement, we had this process going on. I noticed that there was a range of technologies that were not being developed, and so I began to work on something called the Global Apollo Program, and that program took off when President Modi was appointed as Prime Minister. I was in the Foreign Office at that time, and Prime Minister Modi announced in his very first speech on becoming Prime Minister, "I will solarize India from top to bottom," which he had done in the state of Gujarat, where he was chief minister before. So I took him seriously, went straight out to India, had a meeting with the Minister of Environment, then the Minister of Energy, and then I was in the Prime Minister's office all in one day. He loved what I was talking about with this Global Apollo program, which was nations should join voluntarily a group that would provide altogether about $30 billion of public money for research and development into clean energy technologies needed for a world in which we would head towards zero carbon dioxide emissions. Now, this program took off on the first day of the COP meeting. And I won't take you through the massive endeavors that it was to get this to happen, but here is the big moment in the next slide, when each of those heads of governments making this commitment to contribute towards that $30 billion stood under the banner Mission Innovation, which was the name given to the program by Prime Minister Modi, who is there in this list of heads of government. Now, you can also see, I think, a non-head of government there. He's as wealthy as any of the more minor nations. Bill Gates is there because he decided to put $1 billion of his own money into funding the new technologies that emerged from this process to get them into the marketplace. And he had signatures from 28 other billionaires from around the world to back that program. Now, the point is that this is this year a successful program. It's spending $22 billion. And what I'm really saying is, this was a meeting outside the COP process. These people were all there for the first day of the COP meeting when they invited the heads of governments to be there. But we held a separate meeting under the Mission Innovation banner. I'm suggesting that this is a good way forward. Let's get willing nations together to put together the work that needs to be done to manage our challenging process. I'm just going to give you my favorite example of a new technology emerging. It is a British company, next slide, VariaLift Airship, that is producing the airship shown here. It is enormous. It has an aluminium shroud around it. It has got 12 subdivisions. Ever since Titanic, every ship has 12 subdivisions. This one has 12 as well. Everyone inside is the same. It's got an airbag. It's got a cylinder for compressing or helium into or releasing helium from, and it's got a compressor. So you want to lift the airship, release helium into the airbags. If you want to lower it, pump the helium back into the cylinder. And the motors that you see are designed by Siemens. They are electric motors, and it is covered with photovoltaics. It is enormous. So you might see a lorry in the front of the vehicle there. That is an enormous vehicle. This is for carrying freight. The blue section underneath is the freight carrier. It can carry 150 tons of freight. It will lift up very easily by releasing the helium with 150 tons up to 30,000 feet. And it can travel at about 240 kilometers an hour fully loaded, and without a load, it'll travel at about 450 kilometers an hour. So it's not sluggish. It's flying at a very low air density, so there's not much air resistance there. And the idea, of course, is to use this as designed here for freight carriage. If you could move tomatoes from tomato fields in Spain, the idea is that you fill up containers, lift the containers with an onboard crane on the airship into the deck in the airship, and carry them over to Britain and lower them from the air onto the depots of Sainsbury's and Tesco's and so on. The process is much quicker than the current process. It's vastly cheaper, and it uses zero fossil fuels. And the next slide is another favorite of mine. This is a German company that is producing this, Heindel Energy. Professor Heindel is a mining engineer using standard mining techniques. If we take a flat piece of ground, you can mine under the surface earth into the granite below, a cylinder of granite. You free the cylinder, and then when you have an excess of electricity, pump water under the cylinder. When you want electricity, allow the mass of the granite under gravitational force to squeeze the water out through a hydropower station to generate electricity. So this is a means of energy storage for an electric power system. And in this country, I would think we need about 20 or 30 of these each. This would provide energy storage for about a gigawatt hour of electricity, and if it measures about 100 meters diameter and about 250 meters deep. So it's a very efficient form of energy storage, and the first of these is being built in Saudi Arabia at the moment. Now, let me just move you on, because the situation is actually much worse than we were trying to manage in 2015. So the next slide shows you what is happening at the present time to the ice over the Arctic Sea. These are measurements from Peter Wadhams, who many of you may know as a Cambridge academic. And Peter, since 1980, has been making these measurements by getting rides on the nuclear submarines going under the ice across the Arctic Sea. And he has had permission to ride in the nuclear submarines of Britain, the United States, and Russia, and the Soviet Union. I think probably the only person who has traveled in all three nuclear submarine types. And his measurements show something rather disturbing. The loss of ice in volume is showing a very strong positive feedback. So in other words, where the theoreticians had estimated that the ice would cover the Arctic Sea out towards the end of the century, we're seeing that actually, even today, more than 50% of the Arctic Sea is exposed to sun during the polar summer. And what this means is, because the blue sea, of course, has a much higher absorption coefficient for the sunlight compared with ice, the big change in albedo means that the Arctic Circle region is now as a whole heating up at about 2.5 times the rate of the rest of the planet. A very serious issue, as shown in the next slide, in which I've got a composite here. On the left-hand side is Greenland. Greenland's ice is now melting, and the fear is that it's also going to show a positive feedback and accelerate in its melting as it progresses. And if all of the Greenland ice melts, or when it's all melted, global sea levels from that event alone would rise by 7 meters. I'm not going to talk about the Antarctic, but there's also a very severe loss of ice threatening in the Antarctic region, and anticipating, therefore, the rise in sea level by the end of this century at 50 centimeters, which is the old estimate of the IPCC, needs to be figured up towards 2 meters plus by the end of the century if this continues. In the center, we see what's happened to the polar vortex, because the North Polar region, where the Arctic summer sea is exposed, that the North Pole can be a relatively warm area. And when this diagram was produced, you'll see that it was much colder between Canada and the United States at this point. And the meandering of the polar vortex is creating some very surprising changes to the weather in the Northern Hemisphere at the moment. And on the right-hand side is an issue that scientists have been very reluctant to talk about because it's very difficult to calculate. We all know there's enough methane up in the North Pole region as methane hydrates in the ice, and there's a lot of methane captured at the bottom of the Arctic Sea as well, that if all of that methane was released, temperature rise would be in the region of 10 to 12 degrees centigrade globally. And however, what happened in Russia, in the northern region of Russia, Yamal, which is a region which is solid ice, it's methane hydrates are captured there. This region has a small village, and the people in the village reported very loud explosions could be heard from their village. 300 kilometers north of the village, a team that was sent up to examine this from the Russian Academy of Sciences found the craters shown in the next slide. And these craters are still exploding in the polar summer. Each of the craters measures about 50 meters in diameter. On the right-hand picture, you can see the shadow of the photographer on the far side of the crater. And on the other side of the crater, you see his comrades from the Russian Academy of Sciences standing there. This is an explosion caused by a methane bubble formed as methane is evolved from methane hydrates. It's formed well below the permafrost region, and it then blows the permafrost out as water vapor and methane vapor as the pressure of the permafrost it is exceeded by the pressure in the methane. How many of these have occurred so far? It's over 1,000 of these have now happened. Now, the total amount of methane evolved is still much less than the global methane evolution as a whole, but nevertheless, you can see that the real danger is that we might see a very big release of methane from the permafrost in northern Russia and northern Canada. Let me just quickly move on from the story there to what I'm doing here in Cambridge. The next slide. We have established a Centre for Climate Repair within the university, and this centre has 3 major objectives. The centre, of course, alone is not going to deliver each of these objectives, and I'm working on the policy and diplomatic front to get agreement on climate repair amongst nations and states. And I'm also working with universities in many other parts of the world to work with us on these objectives. The first of the objectives is, of course, deep and rapid emissions reduction. If we're emitting 40 billion tons of greenhouse gases a year, which we're doing now, and continue doing that, and it continues to rise, frankly, there's nothing we can do. But if we can get emissions down to close to zero, we can create new greenhouse gas sinks to restore the atmosphere to less than 350 parts per million. Today, so the pre-industrial level, 270 parts per million. Today, we're at close to 500 parts per million if we include methane and other greenhouse gases. The total of carbon dioxide is about 415. So if we include all of these greenhouse gases, it's about 500 parts per million. And we're saying we need to get this down to less than 350 parts per million by capturing greenhouse gases from the atmosphere. We're not looking at any greenhouse gas sinks that are capable of capturing less than 1 billion tons of greenhouse gases per annum, so that when we add all of these techniques together, we could hope to achieve something like capturing 30 to 40 billion tons a year. And if we do that, it would take us about 30 years to achieve the target figure of 350 parts per million. That is too long to refreeze the poles and to refreeze the Himalayas. Himalayas are also losing ice rapidly. So we're also saying that we need to examine and see if we can discover techniques to refreeze the poles. And of course, that is as challenging as it sounds. If I can I'm going to speed up now because my time is, I suspect, rapidly running out. Let me just quickly run through the next slide, please. There's quite a long list of technologies that we're looking at, and here they are listed in full. My favorite is the marine-based technology. 72% of the Earth's surface is ocean, and we need to look at what the oceans can do to contribute towards this greenhouse gas capture. We are looking at all of these from the point of view, next slide, of first of all, technological feasibility, second, scalability. We need to see whether we have CO2 or methane sequestration potential. And thirdly, potential adverse impacts. Obviously, we need to make sure that none of them has any significant impact in terms of the negative side of the process. And on the next slide, my favorite, ocean surface ion fertilization. This is imitating the process when the wind blows over the Sahara Desert, picking up very small dust particles, forms a dust storm, and the wind blows over the Atlantic. The wind dies down, the Atlantic gets a peppering of this Sahara dust. The Sahara dust, red and yellow is the clue, contains a fair bit of iron, and that means that in those, because iron is the one missing nutrient in most of our oceans, in that region where it's peppered, which may be 10 to 100,000 square kilometers in dimension, you get a very rapid greening. And in that green area, plankton is formed. Plankton is the foodstuff for fish larvae. And suddenly within that area, you have an ocean forest full of life. And that forest will attract whales, which will consume large number of fish, typically several billion fish in an area like this. Very big carbon dioxide uptake. And what we believe is that it's possible, but this all has to be checked out, that if we were to green roughly 3 to 4% of the ocean surface every year by dusting it with iron trichloride or iron sulfate or even desert sand, but I wouldn't waste the sand in that way, we could achieve a 30 billion per year tons of greenhouse gas removal. So that is a very attractive technology to look at, but there are potential downsides, and we have to be very careful. I've only got 2 more slides, and the next one is, I think, a very important one, in which I'm saying political actions will be needed to achieve this. It's one thing to have the technologies and the ambition, the other is to deliver. In the past, national actions, as I think I've shown you, have delivered quite a bit that is required. International cooperation, this is the coalition of willing states. I've given you the example of Mission Innovation. The European Union have announced a €1 trillion euro green finance fund over 10 years. These are very good examples of modes of moving forward without having to go through the full global United Nations program. The next COP is, when this slide was made, was anticipated this June, is now scheduled next summer or after that. And my objective now is that we form a global climate alliance of nations and states committed to this agenda I've described to you, climate repair. And that's what I'm working with and on with the states of the United States. We've got 25 willing states in the United States. I've been talking to the Californian governor, the governor of New York, and they represent about 60% of the US economy. Now we need to get a bunch of nations to agree to this. And once again, India and China critical, and I'm going to suggest that the Mission Innovation group of nations would be a critically important group to get together again under this climate repair agenda. Optimistic, perhaps. Necessary, yes. Thank you. I'm going to give that slide a miss.
Dave, that was absolutely tremendous. Thank you very much indeed. Fantastic quantitative science. And what we see much less of is very practical suggestions to do something about it. I suspect there might be one or two questions. If the audience would recall the methods, you can either put your hand up electronically, in which case we'll see you and you'll be able to speak on the online if you wish. Alternatively, you may put your question by tapping in, and I'll do my best to read them out verbatim. Can you read something out verbatim? Anyway, I'll do my best. First of all, I see a question from Mike Bell, who says, I started campaigning on climate change in the 1980s. However, I hear challenging voices. Climate change skeptics claim that the current temperature is no higher than during the Minoan, Roman and medieval warm periods, and that the rise since pre-industrial times ignores the fact that the temperature dropped until the Little Ice Age and has been rising naturally since. Arctic ice was low when Vikings lived in Greenland. Also, the predicted sea level rises have not been observed. Why are they wrong? That's from Mike Bell, Dave, please.
Well, I'm sorry, Mike, but you have just got your figures from a climate skeptic website. And I could bet that the funders of that website are the Koch brothers, who have been putting roughly $1 billion a year into trying to challenge every aspect of climate science. If we actually look at the detailed results emerging from 2,000, 3,000 scientists around the world, they would say complete nonsense. The climate situation today, rising sea levels, absolutely, as the models predicted many years ago, rising temperatures, absolutely, as the models predicted many years ago, the loss of ice over the Arctic region, much faster than the climate models were predicting. So I'm afraid that, if anything, the situation is worse than the climate modelers were predicting years ago. The climate science behind this is not magic. If anyone can find a fault with those equations of Fourier and of the experiments that were performed, that I mentioned even back in the 19th century, they haven't yet set it out in any sort of detail that could be published in a peer-reviewed journal.
That's very clear. And now I see Stephen Temple with his electronic hand up. Stephen, would you like to come in, please?
Hello. I was actually going to ask a question on very similar lines. You look at the Antarctic ice record, and what you see is very clearly a rise in CO2 and temperature repeatedly associated with the periodicity of ice ages. And they go up very steeply, not, I have to say, as far as we have gone, but then they fall very rapidly and you enter a new ice age. Now, what I'm curious about is whether we have any explanation of why that natural rebound occurs, and whether there is any either likelihood or possibly, if you like to look at it the other way around, risk that that may happen this time around.
Right, so your question deserves a very long answer, and
I'm sorry.
I'm looking forward to finishing off that glass of wine. I'm going to say very quickly, of course, we do know why we went through this cycle of ice ages and warm periods, and the ice ages generally last much longer than the warm periods. And this is just because of the oscillation in the tilt of the Earth's axis as it goes around the sun. So we've got this instability, which is a roughly 100,000 year oscillation. And as that happens, basically, because the northern hemisphere has much more land mass than the southern hemisphere, we get this very big change, both in carbon dioxide levels and in global temperatures. So I'm not going to suggest, it's wrong to suggest, that this is a simple model where carbon dioxide drives temperature rise. It's a very strong feedback system in which, as carbon dioxide levels go up, in fact, of course, temperature would rise, but as the temperature rises, more water vapor emerges as the ocean surfaces are warmed up, and this water vapor adds to the greenhouse gas content. You've got a big positive feedback there. But of course, when we go into reverse, as the temperature comes down on the other side of the cycle, we've got a lag in the whole process. So you get both feedback and lag terms. It's simply naive to suggest, as many people I'm afraid have done, that you drive up carbon dioxide levels and that drives up temperature, full stop. It's quite a complicated multiphasic system.
Thank you.
Thank you. And now I've got a written question from AAM. I'm not sure who you are, AAM, but here's your question. Thank you very much for your talk. It was very interesting to hear about technological tools, and I appreciate that these are your area of interest. But given your close encounters with politicians across the world, would you happen to have any thoughts about why we haven't seen an effective international carbon tax put in place yet, or any other economic solutions, such as a serious cap and trade scheme?
Well, that is a very, very important question. The cap and trade scheme in Europe took off in 2004, starting in Britain, and then we took it across the whole of Europe in 2005. We were still in the European Union. And that tax worked quite well for a while. And then when the global economy fell, it just didn't work, because what they didn't do was suppress the caps to keep the price up. So the carbon price collapsed. We have learned that lesson, I suspect, because we've now got a floor tax so that the carbon price can't fall below that floor. Not all countries in Europe have it. France and Britain has got that. So it's much more complicated. And I think one of the problems with a carbon tax is just that word tax. No government wants to be responsible for introducing a big new tax on their voters. And I think this is an issue of the democratic process. And I don't think anyone has formulated a simple way of getting this through. The cap and trade seemed to be attractive because it's driven by industry, it's driven by the banks, but I don't favor cap and trade over a tax for the very simple reason that the banks take their rent on the process. right? Whereas if you have a tax, the money can be used for generating the alternative technologies, etc., that we need. So I think I prefer the tax, but it's not a very attractive way forward. Governments have not responded on the whole well. I think the British government, if I tell you that it's been the best behaved of all countries, it nevertheless has not always been a top leader. I bet it's a surprise to most of the audience here to know that David Cameron created for us in our negotiations, at our request, a fund of £9 billion to assist in the negotiations. That I was never allowed to put that in the public domain. The government was a bit shy of this for whatever reason. But let me say, I think the reason is because the Conservative government didn't believe that it was a popular vote catcher to say we are spending £9 billion over 10 years to see that the whole world gets a climate change response that is fit for purpose. Now, but the reason why we spent that sort of money is the sensible thing to tell you, and that is precisely because the challenges of climate change to Britain, as with every other country, are enormous. The cost to our economy of rising sea levels, when there are storms at sea, there are storms inland, we get fluvial flooding at the same time as coastal attack. We are an island nation and we are severely threatened by rising sea levels, and the cost to our nation would be enormous if we just let it ramp up and up. But no, your question is a good one, very challenging.
Thank you. Now I can see a question from Andrew and a couple more text questions, which I'll read out. But in the meantime, if you're not too shy and would like to put your hand up and come on screen, we'd be pleased to take your questions. But here we are from Andrew. If we were able to green the Sahara, would the CO2 captured more than offset the reduction in heat reflection?
Okay, that's not an issue I've ever thought about myself, but so I can give you an example that I went up to the great dam in Egypt that produces the hydropower that runs the whole country of Egypt, and I was flown over the entire mass of water, which is an enormous area. It runs into 3 countries. And at the edge of that fresh water is nothing but desert. And yet, if you go back in time, the Nile was also surrounded by desert, but on each side of the Nile, you had green areas. And that was from the annual flooding of the Nile. Now, that annual flooding still happens, but it's all held up in the Aswan Dam. And so what happens is all of that fertile soil from Central Africa is now just dropping to the bottom of the dam. So what I wanted to see was to divert the floodwaters around the lake to create a green line around the lake, quite broad, that would enable agriculture to continue and would enable green forests to be grown. So, of course, that would change the climate in the area, because we all know transpiration from plants does change the climate. I'm not sure that it would ever become a high rainfall area, though. So my answer is, I think I would rather use the Sahara Desert for covering it with photovoltaics and generating electricity and funneling the electricity around the world.
Great, thank you. Now I have a question from Paul Klein at Anglia Ruskin. He would like to ask you about COVID-19, but I'm afraid I'm going to edit that out, and perhaps we can get you back another day to talk about that, David, or we'll be here all night. But he also asks, in the context of this particular conversation, how many individual American states would really make a significant difference to your Willing States Coalition?
Well, I think 25 would make a very significant difference. If you take California and New York alone, you would make a very significant difference. But if you add in the other states that are joining in, some of them are small, like Hawaii and New Hampshire, but others are quite significant. I think we've got enough to make a very big difference, but of course we would welcome having more. More importantly, perhaps, now that the COP26 has been postponed until next year, they'll come when the new president will be in post. Otherwise, COP26 would have been under the presidency of Trump, whatever the result of the election. I think that gives us a very different situation where we could possibly just go for a global climate alliance of nations and bring the whole of the United States in.
Fascinating. Wendy Howe would like to ask, do you think that there's any chance that the impacts of climate change could cause a negative feedback loop as growth in the polar regions extend?
A negative impact in terms of the polar regions' extent as we get warming? The extent of the polar regions will contract?
I think what she means, and maybe Wendy would like to just send a note to clarify this, but I think what she's may be suggesting is that as the polar regions get warmer and we start growing things there, is that going to help us at all?
Well, it certainly won't help anyone living in the major cities of the world on coastlines like London, New York, Calcutta. I can go on and on and on. So a very large proportion of the global population is living on coastlines. The reason is because shipping was the major form of international travel in the old days, and that's where cities were tended to be built.
I think that's a no, Wendy. And now Karina Prasad. Karina asks, thank you for a very interesting and enlightening talk. Is there any positive opportunity in the current crisis which could positively impact on the long-term climate crisis? What can governments take away from this? And would a 50% reduction in normal habits be enough to turn the tide on climate issues?
I think that's a wonderful question, and I really have given a whole hour's talk trying to answer that question. So basically, what the current pandemic is showing us is, first of all, last week I gave talks in Delhi, in Amsterdam, and in Hawaii. I gave the commencement address at the University of Hawaii. I couldn't have done that if it wasn't for the fact that I was sitting here in my study in Cambridge, broadcasting to all of these parts of the world. I had a meeting a few weeks ago with the governor of California. I couldn't have had that meeting if I didn't travel out there, show willing, and spend a whole damn week being jet lagged in addition to get there to have an hour's meeting with the governor. So the ability for me to sit in my office and communicate with the whole world surely is a lesson that we have all learned, and we don't need, therefore, to travel internationally as much as I'm working much more efficiently than I ever have done before. But I think we're also learning a much more interesting mode of living. I have a feeling that consumption is going down. At the moment, we are all used to living in a world in which super consumption is what drives GDP growth. Is it really a necessary model? Is it fit for purpose at all in the 21st century for those countries that already have the sort of wealth levels that we all have in the Western world, and that China and India and other countries are rapidly rising towards? So I'm hoping that we can use this pandemic as a mechanism for raising the awareness of the importance of our ecosystems and move towards creating I think today we're still in the paradigm of the Cold War, where it is much more important to have nuclear weapons, to refurbish nuclear weapons, which we in the United States are doing, trillions of dollars going into that. Military and economic growth are the big power systems. 21st century, eco-civilization should be the big driver, in which we're driving the well-being of people alongside the well-being of ecosystems because of our learning that we live with our ecosystems. And if we don't, if we destroy them, we destroy ourselves.
Well, that's pretty blunt, Dave. Thank you. I'm going to put together, we're getting a little bit short of time. I'm going to conflate a couple of questions here from Graham Pembry and Paul Williams. Thank you for your presentation. Could you comment on the reported 40% reduction 1990 to 2018 in GHG emissions in the UK since 1990 and how we might continue? But also, if you could just weave into that, from Paul Williams at Johnson Matthey, from a global warming perspective, what's better, PV or mirrors?
Okay, so the point about mirrors is that's how you would capture electricity in the Sahara Desert. We all know that with mirrors or magnifying glasses, we can create a vast amount of heat. And so if you focus heat onto a point where you want to boil water, you can create electricity in that process. Extremely efficient. If you can use the mirrors to track the movement of the sun during the day, you can create very efficiently a lot of electricity. So I think that I agree with. Sorry, the first question, if I come back to...
Yes, could you comment on a 40% reduction, 1990 to 2018?
How do we continue to grow?
Exactly.
So I believe that we are beginning to crack this process. We were the first country in the world to set up a climate change committee of parliament, and that climate change committee of parliament sets carbon budgets for every 4 years. At the moment, we know what the budget for 2032 is, and they are now working on the budget for 2036, 2040, out to 2050 in order to achieve net zero emissions. The first target is to get all of our electricity without any emissions at all. And as you may know, we are very close to zero coal usage in electricity production. We have now spent 18 weeks without using any coal in this country, the past 18 weeks, I believe. And that's the first time since the Industrial Revolution. Of course, we are still burning gas. We have to see gas as an interim. We are very successfully rolling out offshore wind. And much to everybody's amazement, including mine, offshore wind is now cheaper for new energy installation than putting a new coal-fired power station in place in Britain. And the reason is quite simple. It's because the oil and gas marine engineers working to the east of the country have now flipped over to the west, where they're doing the installations of wind turbines. They know their business extremely well and are doing this very effectively and efficiently. We are now world leaders in installing offshore wind, and the price is, as I say, less than coal-fired power installation. We can stretch on and on the amount of wind energy we get. We could get much more solar than we have at the moment in the United Kingdom. I can look at so many roofs of houses where there's no solar panels up yet. And I think that rolling forward in time, this means energy storage. How do we store energy? Because these are intermittent energy sources. The sun doesn't shine at night. I am aware of that. And the wind, even in the North Sea, doesn't always blow. 2 days in the winter, when famously, on average, it doesn't blow at all. So we need energy storage systems. I've shown you an example of a new technology emerging that can do that. But in the meantime, we've put in the world's longest underwater interconnectors have gone into Norway, where energy is stored in hydro dams up in the high mountains in Norway. And we are similarly in the process of putting an underwater connector through to Iceland, where the energy can be obtained by using geothermal energy from underneath the Iceland. So I think the answer is we will get to that net zero target, but only if we also capture greenhouse gases. And at the moment, the government, through the research councils is funding 5 demonstrator projects in the United Kingdom for greenhouse gas capture. And we here in Cambridge at the Climate Repair Centre are applying to be the hub to oversee the work of these 5 greenhouse gas capture demonstrators.
Dave, thank you so much. What a perfect note to end on, and bang on time, of course. I'd like to thank you for an absolutely model CSAR evening, full of hard science, full of practical suggestions, and the questions taken in a masterly fashion as ever. Thank you very much indeed. We'll be in touch with you on other matters, I'm sure. But I don't know whether we can play the applause sound, but maybe at the end of this we'll do that. I'm sure you can hear people all around the country, if not the planet, clapping in their front rooms. So thank you so much indeed, David.
Could I come with one simple comment? Could I congratulate Marina on her presentation? I thought it was wonderful. I was captivated.
Thank you very much. Thank you.
There we are. Well done, Marina, indeed. So thanks everybody for being involved. Just a few parish messages as usual. A video recording of the lecture will be available shortly on the CSR website and on YouTube, where you can have a look. I think there are 1 or 2 other things to tell you. Yeah, the feedback. Many of you are very punctilious in sending us feedback. That is extremely helpful. We read everything and take it very seriously. Please respond and help us to improve things in the future, although I'm not sure we can do much better than Marina and David have done for us tonight. So the other thing is to mention that, as we hinted at before, we think there's an opportunity for CSAR to contribute by running different style of activity, maybe around lunchtime, panel sessions, using people who are nearby and who we can interrogate on matters of topical interest. Again, we'd be interested in hearing your views on that. We're already starting to shape up practical ways of delivering that. So our next meeting, if you can call it a meeting, is on the 1st of June. The first smart rugby ball, with or without people spectating, presumably. And Pete Housemeyer, I should say, from Sportable will be talking to us. That's all for tonight. Thank you again to Marina, to Sir Dave, to all of you participating, and we look forward to seeing you next time. Thank you and good night.